Hey everybody, it's NetworkBret. I'm going further into IPv6 today. Enjoy, this is part of the deep dive. So IPv6 continued, and so there's some special addresses. There's a lot of addresses that are predefined. I don't even think I could go over every single one of them, but I'm going to go over some of them. Going through the book IPv6. I forgot, but I mentioned it's in the first video. I'm re-explaining it in Neanderthal English like people enjoy. That's pretty much the premise of my channel. I'm trying to take these concepts and make them more digestible for everybody and for myself. So, if you want some Neanderthal English tech stuff explained, that's what I'm here for. So, the unspecified address is all zeros. It can be shortened to just this, which I find hilarious that it could be shortened that much in IPv6. It's used in the absence of an address, can be used by hosts in the initial boot process or to tell a program that any IPv6 address will work. The loopback address, everyone who's been in networking any amount of time knows that an IPv4, it's 127.0.0.1, but in IPv6, it's all zeros, then a 1, or just this shortened. So these are very convenient. You could just type that or, that. Very simple, very easy. I think it's definitely an improvement. So some transitional addresses, and these aren't always used because while the transition from IPv4 to 6 is not complete by any means, a lot of places have started adopting it, so this is a little less common, but there's IPv4 compatible IPv6 addresses that have been depreciated. But this was used to tunnel 6 packets over the IPv4 infrastructure. And very, very simple format. Again, they made it very easy where it's just all zeros and then the IPv4 address. Very simple. There's IPv4 or IPv4 mapped IPv6 addresses used to represent the address of an IPv4 to an IPv4 only node. And this format's a little different. Instead of the zeros for the 16 bits, you'll see the Fs. So pretty simple. ISOTAP, this one took me, I was reading this page like 10 different times. Like, what? This is Intra-Site Automatic Tunnel Addressing Protocol, or ISOTAP. And it's an automatic tunneling mechanism for nodes that are separated by IPv4 only infrastructure. It treats the IPv4 infrastructure as if it is a large tunnel in between nodes. The identifier is 405EFE for private and 405EFE for public. Those are the same. I might have messed that up. Let me see. Yeah, see, I think one of these is, I think that one's 2 actually. 02. Oh, I'm in I'm in read only. But I'm pretty sure this one is 02005E. And the Internet Assigned Numbers Authority owns the organizationally unique identifier, um, which is what you see. So the prefix, 64 bits, then it has the 005E FE or 0020 or 02005EFE. One is for private, one is for public. I'm almost sure that 2 is for public, even though I have it written wrong here. And then it has the IPv4 address. So you can see here, we're using this as an example, 192.168.0.15. And this would become, if you're using the private one, so these zeros 5EFE, this would become this. So you just add the prefix, you add the middle part, and then you add the IPv4. So I mean it's very, very simple. You could also use the hexadecimal for the IPv4. So the hexadecimal of this address would actually be C0A81. And then the link local would be a link local address FE80, then all the zeros in between, and then the 5EFE normal stuff, and then the IP address, if that's making sense. Now you could also make this IP address on the link local one with the link local prefix. You could also make that CO A81. So fairly simple format. This is for if they're going over an IPv4 only infrastructure. They're basically going to use that as a tunnel. There are Teredo addresses, and sorry, some of these are ugly. PowerPoint sometimes makes it very hard to make these graphics. Teredo addresses are designed to provide connectivity to hosts that sit behind one or two NATs, so network address translations. This is accomplished by tunneling IPv6 packets in UDP. Now, this is almost never used because ISPs just started adopting IPv6, but this was originally a thing that was happening where they'd have a Teredo prefix, 32 bits, then a server IPv4 prefix, flags, port, and the client IPv4. So this one needed a server to kind of translate this stuff, but like I said, this is hardly used now. So link local and unique link local IPv6 addresses. Link local addresses are used for a single link. They're great for things that don't need to go over the router, such as a laptop to laptop file transfer at a coffee shop or conference. You meet a friend, you want to share some files, you can just do a link local one. Don't have to go over the internet or anything. Then there's unique local IPv6 unicast addresses, or ULA, that they also call it local IPv6 addresses for short. They just love to complicate things in the naming sometimes. And they're addresses that are globally unique, but they're not routed to the internet. So they're used within a confined set of networks. So where a unique link or a link local address, you would want to use it as for like a laptop to laptop transfer, or basically a one-to-one. The unique one, you could use it across the network. So let's say you have an office space and you want to use this local IPv6 address for only in that office space. So it's not one-to-one, but it's still confined to a smaller network. Then the link local address format is a prefix FE80 /10 assigned through auto configuration. So this one's pretty simple, not too complicated. You have the beginning piece right here. So 1111 111010, that's FE80 if you translate it. Then 54 bits of 0, and then the interface ID, which is 64 bits. So pretty simple. Then the unique local IPv6 unicast address, or the local IPv6 address format, or the ULA, 3 names, 1 thing, has a prefix of FC00, which translates to this for local, or for the unique local, or a prefix of FD00 for a locally administrated address. And the difference between these, they look very simple there, but the difference is the 8-bit. The 8th bit is flipped. So that's how you would remember that. And these must be assigned by configuring local prefix on routers or the DHCP version 6. And if you remember the link local ones, they are where I lost these. Oh yeah, the link local addresses are assigned through auto configuration. These ones you have to assign, or you can use DHCP version 6. So this is the format of a ULA. I forgot what that even stands. Unique local address. See the names, they're just not great. So you have the beginning piece, which is the same for both. The 0 or 1, that's the 8th bit I referenced before. So whether or not it's locally administered would define whether that's a 0 or a 1. The global ID, you're going to use a pseudo-random global ID algorithm to create a global ID. The algorithm uses a lot of different things to make it random, so time, hardware, and other random stuff. Then you have the subnet ID, which is 16 bits, and the interface ID, which is the normal 64. Um, Obviously, I didn't space these graphics equally, so this is not a literal representation. Clearly, the 64 interface ID should be half of it, if that were correct. And just a reminder, these should not be used on the internet. Then every now and then you might see an FECO/10. This is a deprecated site local address. If you're working with some older equipment, I say older but still using IPv6, which sounds newer, then you might see the FECO prefix, and you really shouldn't use that anymore. So, but you might run into it out in the field. So Anycast addresses, they're designed to provide redundancy and load balancing where multiple hosts and routers provide the same service. It sends packets to any address with whichever device is closest. Users using Anycast have no control over how it's routed. That's decided by the routing protocol. This can be an issue if you have like a fragmented thing that you need to send where it's going to send many different packets. The fact that it could get divided on the route might not be best. Kind of want to send those things over the same route if possible. Then there's some different Anycast formats. They're all pretty simple. I have this 0 divided wrong, but whatever. The subnet router Anycast address, you'll have the subnet prefix with it, which is n bits, like a variable, which identifies the link, and then the rest is just zeros. So 128 bits minus the subnet prefix. Now, Anycast that are required to have a EUI64 formatted ID, you have the prefix, then you have, which is 64 bits, of course, because it's the EUI64 formatted one. Then you have the interface ID, which is 57 bits. You can see that this one has a 0 on the 7th bit. Is that the, yeah, 7th bit? That's important. And then the Anycast ID, which is only 7 bits. Then all other types of IPv6 address types, you have the prefix, which is n bits. The interface ID field, as you can see, these are all ones. It's 121 minus n bits, because the prefix on all the other ones is variable. Then you have the Anycast ID, which is 7 bits. Don't overthink this. Just remember that's the format for them. You can configure them later, and you'll get more understanding of them. So, Anycast versus multicast. Anycast is supported by default, while Unicast is not. So, every node or router will support Anycast, where Unicast you have to have it set up a little different. So, Unicast needs a load balancer with a single point, such as an IP. So if you have a website, that'd be a good use case for Unicast, because you can put the load balancer right where all the traffic arrives, right? Where Anycast, it could be many devices to many devices in a network. You don't have the single point. Anycast is redundant by default because it's a group effort, where Unicast would need multiple load balancers for redundancy. So, like I said, if Unicast is all coming through one IP, then you're going to need multiple load balancers to get it to be redundant. So, and Unicast does provide more control though, because you can actually control how the routing works. So that was my my section for today. The next section I think is multicast, so that's a little bit longer of a one. So hope y'all enjoyed it. IPv6 explained in simple terms for simple people like me. You know, I'm a simple guy. Some of this stuff's complicated. Hope you enjoy. If you ever hear any background noise in my video, this one is fine, but she just gets a little cranky sometimes. You want to say hello?